you are responsible for understanding what your acids and bases are. Okay? One of the other definitions that we are, actually before we do that, so what is your definition for an acid? So which of these is an acid? Okay. Your acid is your hydrogen ion donor, and your base is your hydrogen ion acceptor. Okay? We talked about hydrogen ions being called something else. What was that something else? We drew out what a hydrogen ion was, or a hydrogen atom. It is one proton plus one electron. If we make it a hydrogen ion, what does it become? Just the proton. So one of the other definitions that you might hear would be a proton donor or a proton acceptor. They're ultimately referring to the exact same principle. Okay? One caveat with that. That proton that is being transferred is not going into the nucleus. Okay? Because then you're looking at nuclear chemistry. That's not what's happening here. We're looking at that now, proton being on the outside, sharing electrons with another atom. Yeah?
Okay, so proton donor. Okay, so a hydrogen, a base is like OH is a base.
So if we go up to the equation,
it's usually a negative ion, right?
we have our base, which is going to get to the next kind of question with this, and our acid.
So and then the acid is a proton donor. So basically, the base is taking the positive charge, and that's neutralizing the negative charge.
Yeah.
And then opposite with the hydrogen, it's, well, no, wait a minute, it's a donor. Okay, it's giving away a proton.
Yep.
So it's becoming neutralized too, or it's becoming...
So, and this is where you got to be a little bit careful on what exactly is going on with your neutralizations versus not. Because if we look across the reaction, do we see any charges?
No.
No. So it's very hard to say what charge is neutralized. So you did get at a good point. When we look at our base, okay, or even for that matter with the acid, what part of HCl is dangerous? The hydrogen ion. So what can we say about the chloride? It's useless. So we're looking at H+. What part of NaOH was dangerous?
H, hydrogen.
Of NaOH, our base.
NaOH.
The OH, which had what charge? Negative. Okay? Which means when we go over to the other side, we can ignore that species altogether. What we've just done is converted the molecular format into the net ionic format. And in the net ionic format, that neutralization name makes a lot more sense. Do we have charge on the reactant side? We have a positive and a negative. What do we have on the product side? No charge. It's now H2O. There's no charge associated with it. We have neutralized the charge. And that's ultimately where that name came from. Because we don't look at the molecular format. We tend to look at the net ionic format, just where the chemistry occurred. The sodium and the chloride don't do any real chemistry as far as this reaction goes. You notice that we do pair them up. Okay? In all of your reactions throughout the semester, what's the charge of all of your products? It has always been a very particular charge. What's that charge? Neutral. It has always been 0. Okay? The reason we do that is because we can now say, when you predict products, what's the charge of your product? Neutral, every single time. That's not always true. Okay? So what we're sticking with is kind of a general overarching view saying this is the way it's going to be because it makes things easier for you. You don't have to work as hard. You don't have to know as many of the nuanced rules that you would see in 152 and in organic. Okay? So what we're trying to do is simplify that to a certain extent. But that then also gets rid of some of the reasons behind the name, like the neutralization. It's a neutralization because we lose that charge. Well, if we run based off all the rules that we've been teaching, you don't have charge. So you can't see the neutralization of that charge. Kind of makes sense? So when we go through to predict these products, what we're trying to do is evaluate what chemistry is occurring. The chemistry that's occurring is the new bond that's formed. Okay? Why are we concerned about the HO bond but not the NaCl bond? What type of bond is the HO bond?
Hydrogen bond.
Careful, hydrogen bonding is a force, not a bond. It's a covalent type of bond. It's a polar covalent bond. What type of bond is there between sodium and chlorine or chloride? It's an ionic bond. Which bond was stronger? Our polar covalent bond was the stronger bond. Okay, why is that important? Well, if we're going to run a reaction, which one do we care about? A very weak interaction or a strong interaction? We're focused on the strong interaction. So what we're looking at here is the formation of that polar covalent bond, which was a stronger bond than the ionic bond. Okay? Because there's more sharing of electrons in that situation. So we don't care about the sodium chloride. How do we know the sodium chloride is a weak bond? Beyond it being ionic. This is a water solution. We put this all together in water. What phase do we put on the sodium chloride? Why is it aqueous? Why is it dissolved in water? So there's two rules we could run with. We could run with the halide ion, which I would argue is the harder rule to remember, but apparently you've got it remembered, and I vaguely have that remembered. Your halides are always soluble unless they're bound to silver, mercury. Anybody know the rule? Can I just make it up? Halide ions are always soluble with the exceptions of silver, I think mercury, and one other in your list. The reason why I don't like that one is because I had the exception one, and I very clearly don't have it memorized. What's the one that is always soluble, no exceptions? Group 1 metals. Where is sodium? It's a group 1 metal. Okay? So you're right, halides does work to get you to this aqueous situation, but I think that's a lot more difficult to remember because you got the exception rule. If you remember your group 1 metals being soluble, that solves a lot of problems. Okay? We don't have to worry about the chloride. We don't have to worry about any exceptions. Okay? So when it's aqueous, what are we saying? Well, if it's an ionic compound and it's aqueous, it dissociates into the ions. Well, how strong was the bond between sodium and chloride if as soon as we add water, it breaks? Couldn't have been that strong. All we did was add water. Okay? I mean, we're a lot stronger than that. You add water to us, and we don't break often. Okay? So what we're looking at is trying to see those definitions and kind of apply them. So there's a couple things that we want to tack onto this to help you identify what is an acid and what is a base. Okay? I did hear one float out already for your bases. For them to accept a hydrogen ion, what charge do they need to be? Negative. Okay? Because the hydrogen ion is what charge? Positive. So to accept a positive, we have to have that opposite charge attraction. It has to be negative. Okay? We can take that a little bit further, at least as far as your final goes, and we can go all the way back to the Arrhenius definition. And our Arrhenius definition for a base was the presence of hydroxide. If we have hydroxide, we have a base. What's the charge on hydroxide? Negative. Still matches our definition. Okay? So what about our acid definition? We want to adjust that and tweak that a little bit. Okay, so for instance, if I draw up, let's do this one, and this one. Okay. Let's add an extra little layer of information here, because how do we know we have an acid? Aqueous, so none of those have phases specified, so let's add that little quip to it to make it a little bit more difficult. So, to know we have an acid, yes, we should see the aqueous. So now all of these are aqueous. Are all of these acids? No. Okay. What else do we need to make it be an acid? hydrogen, and aqueous officially. All of these have hydrogen, all of these are aqueous. Still didn't work. So we need to fix our definition a little bit more. Sorry, I'm going to rewrite that a little bit. Which one of those is the acid? Only the middle one is an acid. How do you know the middle one's the acid? We can identify our acids by looking for the aqueous, and that the hydrogen is located in front of our formula. There is one kind of weird exception to this, and it's not a super exception because it's a weird molecule to begin with. H2O. That does have a hydrogen in front. Technically, that is an acid. Unfortunately, technically, it's also a base. So water's kind of a weird molecule. It does kind of shift both between being an acid and a base, okay, which is one of the reasons why it's an awesome solvent, because we can get both characteristics coming out of it. Okay? Whereas our other compounds, we only see these defined separately. Okay? So what you need to look for if you're going to try and identify an acid is to see that aqueous symbol and look for that hydrogen in front of your formula. If it's there, you're looking at an acid. Is that always true? Absolutely not. Okay? Is it true enough for this class that it will simplify and make your life a lot easier? Yes. That's what we're trying to get through. Okay? In future classes, we'll add better rules in understanding what makes it strong and weak so that you can then decide, is that a real acid or is it not? Okay? At this point, we're trying to avoid going into those rules because it's outside of the scope of the class. Okay? So what happens now, we understand what our acid is, let's take a look at potential bases. Okay, bases, we don't get that special naming that it needs to be aqueous, though really what we're looking at in all of our situations is they would be aqueous, but it's not going to help us out. So let's just make them aqueous and kind of ignore that for the moment. Which of these is a base? Okay, it's kind of unfair. You had lab with me this morning. We went through it in lab. We need OH. So that's usually a red flag. Everybody jumps on OH. It's not OH that we're looking for. What is it that we are specifically looking for to identify that it is a base? What's the name? OH is the symbols. What's the name? Hydroxide. What is the charge on hydroxide?
-1.
Negative. How did it get negative? It had to take electrons from something. Okay? The only thing, as far as you guys are concerned, that oxygen can take electrons from is a metal. If we go through and look at our two compounds, what is the OH attached to? Well, in this case, it's lithium. Is lithium a metal? Yes. We now have a base because we have hydroxide. What is our OH attached to in the next one? It's a little bit gray area for you, but
There's a non-metal.
those are all non-metals. Can the oxygen take the electrons to make it hydroxide? No. We see OH. It is not hydroxide. For it to be hydroxide, we have to have that metal, or at least a cation. The only other cation you are responsible for that is a non-metal is polyatomic ion. The one nobody sees because it's the very top of your table of polyatomic ions. Ammonium, NH4+. That is the only non-metal cation. Okay? So if we either see NH4+ or we see a metal. Otherwise, it's not a base. Okay? Again, not 100% true. For the sake of this class and the scope of this class, that's perfect. Works out well for us. So which of these two compounds was the base? Top or bottom? Or both?
Top.
Just the top. Okay? So you have to make sure you understand what's going on within each of those rules and being able to apply those categories appropriately. Okay? It's not just OH, it must be OH minus. Has to be hydroxide. Okay? So Sorry, were there questions on that? Now that I deleted everything? Okay, so conjugate acids and bases. What's happening with our conjugate acids and bases? In this case, what we're trying to look at is evaluate what our products could potentially be in this. And yes, these two examples are a little bit odd for you. Okay? They're ultimately 152 examples. Why are they odd? Okay, what we just talked about earlier. What's the charge on all of your reactants always? Neutral. What's the charge on all of your products? Neutral. What's the charge on the reactants in both these equations? Not neutral. Okay, so these examples are a little bit off, but we're not trying to figure out this balancing thing. What we're trying to do is predict the products here. So it's a slightly different situation where we can kind of get away with it. So what we can go through and do is now define these species to act as something. Okay? In the first case, the HSO3 minus, I'm going to tell you it acts as an acid. Well, if it acts as an acid, what does the water have to act as? It must be a base. Otherwise, we're not doing that reaction. Okay? And we're not trying to trick you here. What do acids do? What is the definition of your acid? Gives up a proton. So if I'm going to predict what happens to that acid structure, what should it look like in the product? Should it have that hydrogen anymore? No, because it lost the hydrogen. What happened to the base? It has to gain a hydrogen. Where did it get that hydrogen from? The acid. So what we're doing is applying those definitions to be able to predict what the possible products might become. Okay? So here's the next kind of layer of difficulty on top of this. The general process, we just remove the hydrogen. Okay? Is that structure correct? Okay, let's take it a step further. Let's add our hydrogen to the other one. Would my answer be correct? What's wrong with it? It's missing the charges. Remember, as we go through a reaction, we can't create or destroy charges. The charges must be the same. What's the name of that SO3? As it's written, what's the name of it? Sulfur trioxide. Somehow I went from a charged polyatomic ion to an uncharged neutral compound? That seems a bit odd. What happened in the course of it acting as an acid? It lost what? H plus. It lost a positive charge. It started as -1. If we lose a positive charge, what happened to it? It became more negative. So now instead of it being -1, it needs to become -2. What happened to our H2O? We added a hydrogen to it, so it became H3O. But did we add just hydrogen? We added hydrogen ion with a plus charge. So if we start neutral and add a positive to it, what charge does it become? +1. Now if we go through and compare our charges, does our charge balance? Yeah, we're now set. Okay. The next example in our lower left hand is now taking, you'll notice, the products from our previous case and turn them into reactants. What would our SO3 minus 2 act as in this case? Why should it act as a base? It doesn't have hydrogen. It cannot act as an acid because it doesn't have the hydrogen. What would we expect of our H3O plus? Well, if we know the first one's a base, the next one needs to be an acid. Why would we expect H3O plus to act as an acid? Do we like charged structures? No. So we want to get H3O plus to look neutral. To do that, I have to get rid of a positive charge, and I can do that by, what was your answer, Sean? Getting rid of hydrogen plus, which means it would have to act as an acid. So what we end up doing is applying our rules, or those same definitions, to now each of these reactions. And we can go through and try that same prediction probability that we went through and did previously. And we're going to run single atom in this case, which is, again, not what you're used to doing. but we're trying to serve the example here. A single acid-base reaction not doing the full neutralization. And we can predict those products. Why show both of these equations? Okay. Is there anything else that's different about these reactions that we haven't seen before Tuesday, really? The arrow that we've shown in there is not our standard arrow. We're not looking at a single directional arrow. We're looking at a reaction that goes both backwards and forwards. That is drastically different than anything we've looked at before. In the equations that we wrote out, we looked at reactants being on what side of the equation? Left in both cases, and our products being on the right. So to draw both of these reactions out, we can go through and define each of these things, but we had to draw two equations. What we could have done instead is just drawn a double arrow, saying the reaction goes both forwards and backwards. Ta-da! Now I don't have to draw it twice. I draw it once and just use two arrows. Okay? So it simplifies some of my work as far as writing things out. It also adds an extra kind of layer beyond this. If we go back to our top equation, HSO3 minus should act as, or sorry, I'm looking at the bottom one. SO3 minus 2 should act as what to do the reverse reaction? How do you know it's a base? For the top one. How do we know SO3 minus 2 needs to act as a base to do the reverse reaction? We just worked it out. SO3 minus 2 had to act as a base. Okay? So that becomes a base. What does H3O plus have to act as? An acid. Again, we just worked it out. All of that information is supplied within those two equations, now condensed into one. The reason it becomes confusing is now I ask, where's the base? Which species is the base in this equation? We have to specify both, which is very odd because we're now specifying a product to be a reactant, because we really only react acids and bases. Okay? Which is an odd thing to go through and say, but that's what we're trying to get at. When we look at these double-headed or bidirectional reactions, they go both directions. We no longer have a solution of reactants and products. We have a single solution, and within that single solution, there is a balance of reactants and products. They're both competing with each other, competing for that same space. Okay? If we want to go through and add another layer of information into this, this is where we come up with this conjugate partners idea. We want to specify there's a slight difference between the two bases. Okay? To do that, we can now label one as a conjugate base and one as a conjugate acid, which is really the appropriate way to do that. And our conjugates, 9 times out of 10, are based on our product side. Okay? And I say 9 times out of 10, any ideas why? Because for some reason that one time shows up on the final. So if you are asked to identify a base, how many species need to be identified as bases? 2. Okay? And if I now ask you for the conjugate, okay, that one becomes a conjugate base and this one becomes a conjugate acid. How many conjugate bases and conjugate acids are there? 2 of each of them. Because our conjugate is always on the product side. Which side of the equation is our products? Both sides. It all depends on which way our arrow is aiming. Okay? It's one of the things that makes our acid-base reactions, particularly weak acid-base reactions, trickier. Okay? This reverse or bidirectional effect is known as equilibrium. Okay? And we'll talk about equilibrium in a second here. How complicated is the topic of equilibrium? Think the entire semester that we've spent over all the broad topics that we've looked at. 152, so second semester general chemistry, is all about equilibrium. That's it. Okay? We spend an entire semester going over what are the dynamics of equilibrium and how can we manipulate and use it. So it is not an easy concept to get or grasp. It takes a lot of practice to be able to work with it. Okay? So, understand what your bases are, understand what your acids are. Why do we add the conjugates in there? What is the conjugate partner? Okay, so if I'm now asking for the partner for that conjugate base, what is its conjugate partner?
Would have to be the acid, conjugate acid.
You need to give me a little bit more information. If you just say acid, I'm thinking HSO3 minus.
H3O positive.
Okay. What does conjugate mean? Think conjugal visits. Who can have a conjugal visit?
On opposite side, opposite sides of the reaction.
Conjugal visits are something where you're looking at someone that has some relationship with the person in prison, right? Okay, on the opposite side of the wall. If we, right? It is just prison, isn't it? Yeah. Okay. Just checking. Okay, if we take a look at the conjugate base and the conjugate acid, are they on opposite sides of the wall?
No.
They're on the same side. They're both on the right side of the equation. Okay, so our conjugate partner of SO3 minus, or SO3 minus 2, has to be on the other side of the reaction. Which of them is it?
HSO3.
Why is it HSO3 minus and not H2O?
Because it's the H2O is not similar to the.
It comes to similarity.
Yeah.
Okay? Our conjugate partners are the most similar species on the opposite sides of our wall, or our opposite sides of that reaction. So our H2O's conjugate partner is H3O. Okay? Notice as well, our conjugate partners. One is a base, one is an acid. Both cases. Okay?
Is that always true?
That is always true. Okay? Questions about your conjugates, acids and bases? Okay, we will come back to acids and bases here in a second, but I want to go into equilibrium. What happened? Oh, it just said conjugates. Okay, so we've got that double-headed arrow, which is bringing up this concept of reversible reactions, which means we don't have a reactant, we don't have a product anymore. We've got this mix. And the example that we showed or discussed, what was it, Tuesday, we looked at a seesaw, right? We said we put the fulcrum right in the middle. Well, one of the things that's interesting within chemistry is our reactions all have almost their own artificial intelligence. They always strive for equilibrium. They want this balance. Okay? That does not necessarily mean that the concentration of products is the same as the amount of products is the same as the amount of reactants. Because if that was the case, we get kind of boring chemistry. Okay? Our reaction gets to decide, okay, before it even occurs, where to set that fulcrum. So that is decided by the reaction. Okay? Equilibrium is the point where these two balance out and our, what is that, lever, is level. Okay? At this point, do you think we're at equilibrium?
No.
No. We've got way too many reactants or way too few products. So what could we do to make it at equilibrium? Think simple first. We could add more products. All right, so now we've reached equilibrium. Okay? So the weight on our product side can now lift up at the other end because of that whole lever dynamics from physics. Everyone okay with that? Okay. So what Le Chatelier went through and did is said, okay, I've got this reaction that favors products, but I'm greedy. I want more products. Okay? So he wants to come up with some way that he can try and get more products to form. So hopefully what we're trying to do is tweak the dynamics of the reaction. So he said, okay, well, what happens if I go through and add more reactants? Okay, so remember, our experiment is now at equilibrium and happy. So Le Chatelier says, let's mess with it a little bit. Okay, just like we do in this class, right? You finally get it, you got it, you're happy with the concept, and then what do? Whoop, try a new concept. All right, then you get it, you're happy with it, what do? Mess with it again. till ultimately, hopefully by the end of the semester, we get to the final and everything's now reviewed. There's no more blankets being pulled out. You're ready to go and you're fully tested on everything you've seen.
You're totally burned out.
Okay, and you're totally burned out. That's what a semester will do. Okay, just be glad it's not a quarter system. It's even worse. So, the Chatelier comes in, says, okay, I'm going to add more reactants. What happens? Is it at equilibrium anymore? Okay, we put more stuff on the reactant side. Okay, reaction goes, well, crap, I'm not at equilibrium. I have to figure out some way to fix this. Okay, but the reaction's a little bit different than the Chatelier or us. Okay, the reaction can't bring more information in. It can't spit information out. It can only work with what it's got, and it somehow has to find the balance between that material. So what can it do? Okay, as an extra little hint here, when we run our reaction, how do we know it's at equilibrium? What are we looking at for that equilibrium idea? Our arrows. Our arrows are saying what? We're taking some reactants, and we do what to them? Turn them into products. What's the other arrow mean? We're taking some products, turning it into reactants. So what can our reaction do? Same thing. It says there's way too many reactants right now, so I'm going to take a small amount of those reactants. I'm going to cut out a nice little slice of them, and I'm now going to put that slice, try and draw this right, over on the product side. That was drawn horribly, but you get the idea. So what's happened now to our reactants is we've now lost that chunk. We can't destroy matter. What happened to that chunk? It's been converted into products. So we've now added that mass to the product side. Our reaction is going to continue to chip away at the reactants and start making more products until it reaches that final balance and where they equal each other. And now it's back at equilibrium. That guy, French guy, Le Chatelier, thought that was kind of an interesting phenomenon. Okay? We made more products by adding in more reactants. So what happens if now I take stuff away? Or sorry, if I added, let's not do taking stuff away yet. So let's take it all the way back to our equilibrium, where we were nice and happy. And now instead of adding reactants, I add more products. What happens now? Now I've got way too many products. So what do we have to do? We're going to have to take a chunk out of those products and shift them over to be our reactant concentrations. And what happens is that we now delete that section or that mass, and we've again re-equilibrated. We've put ourselves in that position where they can now balance out. That is what equilibrium is looking at. So we put in a stressor. We added something to either the reactant or the product, and our reaction shifts to adjust and account for that imbalance. Okay? It doesn't matter where the reaction slider is or where that lever point is. It's always going to adjust to account for that difference. Okay? So now the tricky one. Are you ready for the tricky one yet? Should we try a different version of it? Okay, I'm seeing a head shake no. So let's try a different way. Let's get rid of the fulcrum idea. Have you guys seen water move before?
Water move?
Yeah, water move. Familiar with how water moves? Everyone's happy with that? I know, it sounds like a silly question. It's going to be kind of important. Okay, we're going to get you to participate a little bit here. Here's our new system. We've got a reaction. Put up a little bridge there. We've got our reactants over here and our products over here. So when we go through to start a reaction, what do? We take our reactants, all of our stuff, and we put it into the reaction section. The caveat that we're going to do here is I can mix my reactants, but the reaction will not start until we say reaction go. Okay? So I can fill this up as far as I want. So I'm going to fill it up to here, okay, with reactants. All of that is reactants. Then what are we going to tell the reaction to do? Oh, you can do better than that. Reaction go. It's going to be a very long class if I just stand here and wave my arms. Come on, I know you guys got it in you. Reaction go. Okay, there we go. Reaction go. What happens? We're going to remove the lever at the bottom. So now the reactants can convert into products. What happens to the level of liquid in the reactant side? It decreases. Okay? So it's going to start to shift over to the products. Does all of the water rush up to the products and we end up with something like this? No, what happens? It balances out so that they equal on both sides. If I take a look at this single water molecule over here, does it stay there? No, it can freely move back and forth. It could go over here, or it could go over here. What does that little symbol right in the middle look like? Looks an awful lot like that giant massive blue and purple circle around our double-headed arrows looking at our equilibrium reactions. Our reaction is going backwards and forwards constantly. We don't start it and it goes, whoop, there's products. It goes backwards and forwards both times. Why does the level not change? Because it is going backwards and forwards. Why does the level of the water not change? It's constantly going backwards and forwards. So if one goes to the product, one goes to the reactant. The rate on switching between reactants and products is equal. How does this apply back to Le Chatelier's principle? Well, Le Chatelier says now that we're at this happy equilibrium, I'm going to say, okay, reaction, pause. And I said at that time, you don't have to say it. So reaction, pause. And now Le Chatelier says, okay, let's add some more reactants. All right, and then you all say, yeah, reaction, start. What is that? Reaction, go. What happens? That purple level is going to drop down, causing our product level to go up until what happens? We reach, good choice of words, a new equilibrium. So what we're trying to do is cause an imbalance between each of these and see how that affects the overall reaction. Kind of a neat process. Okay? So here's the tricky, or think we got the idea now on both backwards and forwards? Okay, so if we added products in now, what would happen? It's going to do what? It's going to have to equilibrate. How is it going to equilibrate? What's going to happen to the concentration of our reactants? The reactants, if we add products. Our reactant concentration is going to have to go up. So if we put in product stuff and we then let the reaction go, it should level off where they're now both equal to each other. Okay? So here's the tricky question. I've been erasing too much on this. It's close enough. Let's get us back to our equilibrium. Chatelier got really, really creative with this. There's certain ways that we can control our reactions to the point where I can remove things from it. Okay? Typically, what do you think we would want to remove? Okay, how do we start a reaction? We mix reactants, right? So if we're going to start a reaction and we mix reactions but remove the reactant, what's that going to do to our reaction? Won't happen because I got rid of the reactant. So typically, what do we try and do? We try and remove products. Okay, so let's pause our reaction, put up our little barrier. Okay, now what Le Chatelier went in and did is he removed some of the products. And now he said, fine, reaction go. Barrier is eliminated. Now what happens? It needs to equilibrate. How does it equilibrate? The reactant concentration drops to fill up the void of where our product was removed. Okay? Why is this concept a little bit more difficult than the previous one? What did we do in the previous examples? We added reactants and products. What's the mathematical symbol for addition? Plus. Everybody's okay with plus signs. What did we do this time? We removed. What's our mathematical symbol for removal? Minus sign. What's been the bane of pretty much everybody's existence this whole class? Trying to manipulate that minus sign. The minus sign is a lot more difficult to understand and interpret. We have to be very careful with our overall interpretations. Okay? So when we're looking at Le Chatelier, we can both add and subtract. We then have to evaluate back in either this method where we're looking at that water level or looking at our balance. Okay? And trying to decide what happens to our equilibrium if we put an extra weight on versus taking a weight off. How do we account for that difference? Okay? And it's tricky to deal with. Okay? That's why it takes a full class. Okay? To make it more difficult, usually what do we end up doing? So all we've done here is just talked about it in general, right? Add 5 pounds. How much does the weight difference? Now you have to account for how does it shift to balance out that weight. Okay? So we'd have to bring in numbers to understand each of these conversions. That number difference makes it a lot more difficult. It's usually why there's a huge drop rate in 152, because the mathematics required in that section involves a lot more detail. It usually throws a lot of people for a loop. Okay? Thankfully, guess what we have to deal with as far as those mathematics go? Not at all, yippee. Okay? So,
what's another term for that? I'm sitting here trying to, we learned something like that in biology, and I'm trying to remember what it was. It had to do with...
Osmosis?
Yeah.
Osmosis is running under a similar process.
Yes,
it's the equilibrium.
that's what it is.
It's the balance between those.
Yes. Right.
And our bodies do the same thing. That's ultimately what osmosis is. It's an imbalance of those ions.
Yeah.
Our body will intentionally make an imbalance. That imbalance it can then take advantage of. Plants do it all the time.
Right.
They absorb light and do what with that light?
Synthesize it.
They synthesize. They don't synthesize light. They absorb that light, but what do they do with that light energy?
Well, it's photosynthesis.
So what is photosynthesis doing?
It's using
Creating ATP.
the glucose.
How does it create ATP?
Goes through the electron transfer chain, Krebs cycle.
What's going on with the electron transfer chain? We absorb that light, and there's now a barrier. It uses that light energy to put a hydrogen ion on one side of that barrier. The other side doesn't have any hydrogen ions. So we have a massive positive charge on one side and no charge on the other. Okay? What we've done is generated a battery. So what does the plant then do? Well, it says, I got a bunch of hydrogen ions. I'm going to control how that hydrogen ion flows across the membrane. Because as it naturally wants to move across, I can take advantage of that flow and generate energy. Much the same way that we take advantage of the flow of water, ultimately from the sky, all the way back down to the ocean. Think about your hydroelectric dams. What's happening? We're taking water from a high elevation. We put a dam in front of it and say, that's fine, water, you can run down, but you got to run through my machines first. And in the process of you falling, you're going to translate some of that energy over to me. Now I can use that as electric energy. Bodies or humans are doing the same thing. Plants are doing the same thing. We're trying to take advantage of the imbalance of those charges, okay? Or make our chemistry do that imbalance for us. Kind of a neat concept. And since we know everything is striving for this neutrality through equilibrium, we are constantly causing reactions to go out of equilibrium. Because once they're out, what are they naturally going to do? Go back to equilibrium. Okay, so it's kind of a neat concept. Really what we're trying to do is ruin all chemistry, which, if you look at it, that's not a bad idea. Let's just ruin chemistry, right? Okay, nobody thought that was funny. I thought it was kind of funny. We look at our acids and bases. Okay, there's another concept behind this. It's not just that we have an acid. Okay, think kind of along the safety lines. If we had two solutions up at the front of the classroom right now, okay, solution of HCl, what color is it? Clear. Solution of vinegar, what color is it? Clear. Take these two solutions, and you now have to put your hand into one of them. Which one do you have to put your hand into? You sure hope it's the vinegar. How do you know it's vinegar? You don't unless we have some other piece of information behind that. So when we're thinking of our acids and bases, some acids are incredibly dangerous. Some acids aren't. Ultimately, what that danger is coming back to is the ability to give up that hydrogen ion to act as an acid. If it can't give up that hydrogen ion, then we don't care, because it's not going to act as an acid. Care about other things, but we won't care about it acting as an acid. Okay? So what we want to look at is the ability of an individual molecule to give up a hydrogen ion. If it gives it up freely and right away, we look at it as a strong acid. If it doesn't give it up freely and right away, we look at it as a weak acid. How do we know if it's a strong acid or a weak acid? Okay? Particularly with those two jars sitting up there. Ding. How do you know? That's kind of a tricky question. Ultimately, what it's going to come back to, equilibrium. Oh, God, let's get away from that. That's numbers. Okay? So let's try something else. Our strong acids have a very particular pattern. They will always completely dissociate into ions. And the interesting property of ions is that they can conduct electricity. So if I stick a battery, okay, that has electricity into that solution, and I've got some wires set up to a light, if it's a strong acid and I dip that thing in, what happens? The electricity flows and I get a light, also known as electrolyte. I completely made that up. That's not true. Well, where it came from, that's not true. But what we're looking at is something known as an electrolyte. Does our solution have ions in it? Does it allow for the transfer of electric energy? Our strong acids completely dissociate into ions, one of those ions being H+, the other one being, who cares, but it's another ion. That's going to allow for the passage of electricity. We're looking at an electrolyte. Our weak acids, if we run the same test, what happens? They don't turn into the ions, which means there's not enough ions to allow for the passage of electricity, and hey, there we go. So we could take our little battery and dip it into those two solutions and say, that light didn't go on over there, I'll stick my hand in that one, thank you very much. Or you can be like, your test is an idiot, and I'm not going to do that. Okay, kick me in the knee and run. Okay, don't kick me in the knee. I like my knees. Okay? Ideally, we have another process that we could try and look at too, on trying to look at individual structures. You don't have to worry about identifying that structural information, at least not yet. For the sake of future courses, what we go through and do is we define them to make it even easier. Okay? So we say the strong acids are a very particular bond type. Those strong acids are listed. So you would have to know them as strong acids. And what are those strong acids going to do? Completely give up their ions? There we go. Okay? What is our weak acid then going to be? These are your strong acids. I give you acetic acid, HC2H3O2. Is it a strong or weak acid? Why is it weak? It's not on the list. That's how we decide between strong and weak. We've got the strong ones memorized. If it's not there, it must be weak. Okay? We run the same idea with our bases. Our bases are going to have that OH, and we're looking at them being partnered with a group 1 or 2 cation. If they are partnered with that group 1 or 2 cation, then they are strong bases. If it's not partnered with that, then it necessarily becomes a weak base. So we're just looking at it, our strong acids, effectively memorizing those and just kind of moving on from there. Okay? As far as what you need to memorize for this test, you don't need that. That's something that you would see in the future. And some teachers will actually have you memorize a few more strong acids. Okay? This by no means is not all of the acids, okay, or all of the strong acids. There are a lot more. Why do we not make you try and memorize more of them? Because there's a lot more. So we pick the ones that you would most likely see, okay, or that we would decide to test you on. So some of those you've seen already. Sulfuric acid you've seen and worked with. Hydrochloric acid you've seen. Nitric acid you've seen. Okay, I don't think you've worked with hydrobromic or hydroiodic. Both of those are even stronger acids. Okay? So we've got this kind of balance between these. So the next issue is what's going on with electrolytes. Okay, this is what your lab today is all based on, or on Tuesday. So what we're looking at with an electrolyte is it's any species that completely ionizes when it hits the water. Well, what happens when something ionizes in water? What are we saying actually happened to that molecule? the bonds in the molecule broke, and if I take solid, say solid sodium chloride, and I add it to water, what would you tell me happened to it? Became aqueous. You guys are picking all the scientific words. I'm a little 5-year-old kid. What happened to it? It dissolved. Okay? So what we're looking at for our electrolytes is an ionic compound that dissolves. So it needs to be aqueous. What if it's an ionic compound that's a solid? Okay? Say like calcium carbonate. Okay? For an electrolyte to work, to allow for that passage of electricity, what do we need to have present? Ions. Take a look at calcium carbonate. Okay, it ends up being a very weak electrolyte, almost to the point of non-electrolyte. Okay, why? You all got your solubility rules memorized, right?
Right.
Carbonate. All carbonates are insoluble with the exception of group 1 metals. Calcium is a group 2 metal. This compound is insoluble, which means what phase is it? A solid. What happens to the bond between calcium and carbonate when we add it to water? It stays the same. Do we form calcium ions? No. If we don't get ions, can we pass the electric current through it? No. Okay? So when we're looking at our electrolytes, they must dissolve in water, so they need to be aqueous. Okay? How do we decide if they dissolve in water? Solubility rules. Okay? As far as the test goes, you've got a list of solubility rules that you should memorize. Okay? As far as your lab assignment goes or any homework assignments, you don't have to have them memorized. Look at the table, apply your table, and decide what phase they are. Okay? So your electrolytes are ultimately just turning into ions in solution. If you get those ions in solution, it is an electrolyte. What would we expect of our strong acid? Say something like H2SO4. What was the definition of our strong acid? What was the definition of our strong acid? Completely ionized, which means we've got ions. If we have ions, is it a strong or weak electrolyte? Strong electrolyte. So we can apply two different definitions to the same general molecule. What about sodium hydroxide? What is sodium hydroxide? Base, take it a step further. What were our strong bases? Hydroxide and group 1 or 2 metals. Do we have a group 1 metal? Yep. We have a strong base. What do strong bases do? Completely ionize, which means we now have ions. Does electric current pass through it? Yes. It's also an electrolyte solution. All right? Why is this concept of electrolytes really, really important as far as we're concerned? Anybody know how muscles work? Okay. Muscles are based off of, well, let's try it this way. Have you ever had leg cramps? What's one of the recommendations they tell you should try and do?
Bananas.
Eat bananas. Why?
Potassium.
Potassium. Why do you need potassium? What's going on with your muscles is a balance of potassium ions and sodium ions. Okay? When we're looking at muscle flexion, what is it? Flexion and extension, thank you. Our body is shifting sodium and potassium ions across a membrane. When we generate enough of an ion charge, what happens? We get a contraction of the muscles. Okay? Or relaxation of our muscles. Okay? How does our body go through and do this? Well, we need to have the sodium ions and the potassium ions. Okay, well, what's the difference between sodium and potassium ions? What's the charge on sodium? Charge on potassium? It's not charge. Charge isn't a difference. What else is the difference between them? Atomic number is different. What does that mean? What happens when we change the atomic number? Protons do change, but the protons don't really do much as far as looking at charge. our electron count gets bigger. How is our body controlling whether we have sodium on one side or potassium? That membrane that separates them is filled with little pores. Those little pores only allow for the transfer of one of those ions based on size. So if you understand something about our periodic table and what's going on with size differences, our body, our chemistries, are manipulating and controlling that size differential to only allow for one to pass through so that we can build up this gradation or gradation across that membrane. Okay? We talked about it with photosynthesis. We're building up a hydrogen ion. Did I talk about it with photosynthesis? Yeah. Okay, with hydrogen ions on one side of the membrane. It is the flow of hydrogen ions back across that membrane. Because that membrane prevents the passage of those hydrogen ions, our body or our chemistry can now decide this is when the hydrogen ion moves. Because I'm controlling it, I can control the energy released by it. And that is what ATP synthase does. Pretty cool little machine. Okay? So it's all going back to these balances of electric charge. Okay? So it's kind of a fun concept. If we looked at something that was a weak electrolyte, we wouldn't have those charges to kind of go through and work with. Okay? Questions about that? Good, because I'm not sure I could make up any more. No, that was true. That was true. Okay? Next, last, or sort of the last thing that I want to talk about is thinking about safety. When we look at that strong versus our weak acids, okay, the strong acid, we still got like 10 minutes? No? Oh, okay. Strong acids completely ionized. So we'd have those ions available to allow for that electric current to pass through. Okay, so that's kind of cool. If we had a weak acid solution, we don't expect to see that go through. But what if I took a lot of that weak acid solution? Okay, instead of just taking one molecule or 3 molecules, I take a ton of that solution. Each of those molecules may not give up their hydrogen very often, but if I've got a lot of them, I'm now going to increase the hydrogen ions in that solution. I would just kind of confuse. Let's try it the other way. Sodium chloride, strong or weak electrolyte? Strong electrolyte, completely dissociates into the ions. Take one molecule of sodium chloride, add it to water. Does the solution conduct electricity now? Not very well, because we don't have the ions to bridge that gap between our 2 electrodes. We need more ions to allow for it. So it's not just if it's strong or weak, but it's also a basis of the concentration. Oh God, concentration. That means we got to deal with molarities. Okay? That gets a bit tedious. Okay? For one kind of reason in particular. How many of you have heard of molarities before this class? Okay, a couple people. How many of you have heard of pH? Oh, interesting. What is pH a measure of? The concentration of hydrogen ions. Why do you know about pH but not molarity?
Well, from a health standpoint.
It has to come from a health standpoint, is ultimately where it's come, is kind of the definition on this. Molarity is the absolute. That gives us an idea on exactly how much there is something in solution. But if we take a look at a solution like the example here, hey, little Timmy, watch out for that solution. That's a 0.15 molar solution. That could hurt you. Okay? But that 0.15 molar solution of acetic acid, that's not that big of a deal. But that 0.15 molar solution of HCl, oh, that's dangerous. What is Timmy going to do? What the freaker's wrong with you? Well, throw them both at you. Get out of here. Okay? We need something that's easy and consistent to understand and get through. Okay? So that when we tell people that you need to watch out for this solution, and they ask why, well, we can say, this number rating is bad or dangerous. Without that rating, we can't evaluate it that quickly and effectively. We have to educate everybody about concentrations and molarities, which I would argue is probably a good thing, but that's a separate issue. Okay? That requires a lot more mathematics. Remember, look, you didn't see it until college when you could have seen it as a 5-year-old. Okay? So why did pH come about? It's trying to convert that concentration, that value, into something that's easier for us to wrap our brain around. Okay, think Avogadro's number. 6.022 times 10 to the 23rd molecules. That was a ridiculous number to work with. So what did we say? Well, that equals 1. Why? Because 1 is a lot easier for me to count on my hand than 6.022 times 10 to the 23rd. What we're trying to do is simplify those numbers into something that we can comprehend and get through. Okay? So this is where pH came from. Okay, well, what does pH really do? Well, it's a measure of the acidity, or the concentration of hydrogen ions, both low concentrations and high concentrations. Okay? And it's really based on water. Okay? At low pHs, is it acidic or basic? Don't look at that one. It's acidic. Okay? At high pHs, it's basic. Okay? Well, I said it was based on water. Okay? But it's still always H+. It's still always hydrogen ion. What happens when water dissociates into ions? Becomes H+ and OH-. What was our definition of an acid? H+. What's our definition of a base? Our horrible definition was OH-. Water is both an acid and a base. It releases both of those, which is why water is pretty much our central molecule for a lot of our chemistries, because it's revolving around that same concept. Okay? Yeah, it's shockingly amazing. Okay? So if we go through and take a look at a low pH, what we're saying is we have a lot of H+. What does that mean about the OH? We're going to have a very small amount of the OH-. Why? Because if we had a lot of it also, what happens? Neutralize, we've got water. So if we have a low pH, we have a lot of H+ and very little of the OH-, so it can't neutralize it. What happens when we get up to a high pH? We have a very small amount of the H+, but to have a very small amount of the H+, we're necessarily going to have a large amount of the OH-. So our pH scale, even though it measures, only H+ concentration, allows us to look at both acid and base solutions. And we can now go to Timmy and say if that solution pH is really, really low, that's bad, don't touch it. If it's really, really high, that's bad, don't touch it. There's no more watch out if it's this substance or this substance. We don't have to educate on all of the possible acids and bases. We just have to say that range is bad. Okay, well, opposite of bad, we need a range that's good. What's our good range? 7. 7 is absolutely neutral, and our 6 to 8 range is stuff that we work with nearly every day that we're probably eating and consuming. Okay? So in that range, if we see a solution that says pH 6.5, probably not that dangerous, at least as far as our acid-base chemistry goes. Okay? So that helps us out as far as simplifying and educating people about safety. But now the question, where did it come from? I said it is a measure of concentration of our H+. But our H+ is always going to be this weird molarity number that could range anywhere from a very, very small number, very close to 0, to a very big number. Probably get up to like the 16 molar range, maybe 32. Okay? How can we convert that 0 to 32 number down into this range? Anybody know what the P stands for?
Minus log.
It's the negative log. So if you want to figure out the pH for any solution, what do you have to do? Go to your calculator, hit minus sign, or sorry, not negative, but minus, the plus minus thing, to get the negative sign, log whatever the concentration of your H+ is. Return, there's your pH. Okay? So we can convert numbers that look very odd and difficult for us to manipulate and work with now into a scale that's between 0 and 14. We don't have to worry about where it came from, because if it's there, it's dangerous, period. Okay? So that simplifies our safety, our review, our outlook on our acids and bases, and that's pretty much the end of everything that we're going to be talking about. Okay? So I did say that we were going to talk about some other stuff. We didn't get through any of the review slides. Ultimately, all those were copied and pasted straight from the other slideshows. I would recommend that you at least click through them because these are the ones that I think stand out. You're looking at 40 slides. A little bit less than 40, looks like 35 slides. You should go through and at least review the topics on each of those and make sure that you remember those kind of pieces. 40 slides, for those of you thinking that's a lot, 40 slides is a whole heck of a lot less than the 300 pages or so that we covered in the textbook. Okay? It's also 40 slides where you're probably looking at 1 to 2 questions based on that slide information on your test. So it should help you kind of review for the test. Now questions, and for sure you had a question, so what was your question number? 63.
No, wait. Yeah.
I personally kind of dislike this question because I think it could be phrased a lot better. The question is, what is the percentage of water in this compound? What is the percent H2O in, it's officially borax, but that's the name of the compound. What do we have to do to figure out a percent? We need the mass of water, and we'll divide it by our total mass. Okay, and then officially, just in case I'll forget it, times 100%. Okay, how do we get the mass of water?
You're basically looking at 18.
So the mass of H2O, we've got 2 hydrogens, so 2 times 1 plus 1 oxygen. That was a horrible parentheses, sorry. Times 16. And I did hear an 18 there. You're right, that does equal 18. Is that the number that you should be using for the mass of water? Why times 10? There are 10 molecules of water in that formula.
Oh, yes.
So it's having you evaluate what that formula means. So this really is a 2-part question. Do you understand what the numbers in the formula mean? Do you know how to get molecular weights? And do you know how to get a percent? Okay? So we multiply by that by 10, we should get 180. How do we get the mass of our total? So we'll add up everything. 2 times 23 plus 4 times 10.8, thank you, plus 7 times 16 plus why 180? Because there's 10 waters, we already calculated that. We can just add that in there. That'll then give us our total mass. 180 divided by that total mass times 100% gives us our answer. Okay? With the percent questions, I did see quite a few of those show up within the practice final, and maybe 1 or 2 within the exam itself. If you've got questions about what type of percent they are asking for, please ask. Okay? In my opinion, I do think you can determine what percent they're looking for by carefully reading the question or answers. What do I mean by what percent? There's a percent mass, there's a percent volume, there's a percent yield. Okay? All of them are ultimately the same type of calculation, but will give you different numbers. So if you aren't sure which one to use, raise your hand, I'll come by and say this one's percent mass. Okay? If I get enough people asking the same question during the final, it will get written on the board. If it's only one person, I usually don't write it on the board because then I kind of run under the assumption that only one person had a problem with that. Do you guys have any issues with that? Or if I get a question, I give an answer, I should write it on the board, period. Okay, I'll write it on the board anytime I get a question. Okay? You can ask multiple questions. It doesn't mean I'll give you an answer. So the only time I'll write it on the board is if I'll give out some extra piece of information. Okay? Should I announce when I post things on the board? That's the next big question.